So that's what this chapter is about, counting. We need to find a way to count the total number of outcomes. It was kind of easy to just list all the ways that I could roll a 7 on 2 fair die, but sometimes it's not going to be easy to be able to count that. And then being able to count the total number of ways, all possible outcomes. So we need a couple of techniques that we can use to do this counting. But first of all, we're going to talk about a couple of operations. And the first operation is going to be multiplication, or the product rule. So we're going to use the multiplication or the product rule to count sequences. If I have a sequence of separate tasks that I can break a procedure into. So we're going to break the procedure into the individual tasks, then we're going to multiply the answer or the probability of performing each one of those tasks. So let's say, for instance, that we have 2 tasks that have to be performed. We're going to call these 2 tasks task 1 and task 2. So if there are n ways to perform task 1 and there are p ways to perform task 2, then there are n times p ways to perform the entire procedure. Think of a sequence of tasks. We have to perform each one of the tasks in sequence. I have to perform task 1 and I also have to perform task 2. This logical AND is going to be multiplication, so I'm going to multiply the 2 of them together. We have seen this before when we were rolling 2 die. We were trying to roll a couple of 3s on a pair of die, and we said that there were, if I'm rolling the first die, there is only one way that I can get the first 3, and there is only one way that I could get the second 3. That gave me 1 times 1. If I went into the denominator for all possible ways, we said that there were 6 ways that I could roll the first die, and there are 6 ways that I could roll the second die, which gives me 6 times 6. That's where we got our 1 times 36. Because if I'm rolling 2 die, I have to roll the first die, and then I have to roll the second die. This is a sequence of events. And whenever I have a sequence of events that have to be performed, I'm going to use the product rule. So let's look at a simple example of this. Let's say, for instance, you've been tasked with labeling all of the chairs in an auditorium. And you're going to have to label the chairs with a capital letter and a positive integer that does not exceed 100. So how many different ways are there for me to do this? How many chairs can I have in my auditorium? Well, I'm going to break this into 2 tasks. The first task is going to be assign a capital letter, and then the second task is going to be to assign a positive integer, 2-digit integer. All right, so the question is, how many different ways can I assign a capital letter? Well, I'm pretty sure that we have 26 capital letters in our alphabet. So how many different ways can I assign a 2-digit positive number? It would seem like there are 100 different ways for me to be able to do that, 0 to 99. So I'm going to take task 1, I'm going to multiply it by task 2 because both of them have to be completed, which is going to give me 26 times 100, or 2,600 different ways that I can do this. That means I can have 2,600 chairs in my auditorium. So let's try this with license plates. For instance, you are the DMV who is tasked with assigning out license plates, and you are going to have, your state has license plates with 6 characters. And the state has decided that they want these 6 characters. The first 3 are going to be letters followed by 3 digits. So that begs the question, how many different unique license plates can you have? Well, I can actually define this as 6 separate tasks, mainly because there are 6 characters that make up a license plate number. So I'm going to lay out the 6 characters of the license plate number, and I'm going to label this task 1 and task 2 and so on. And then I'm going to see if I can figure out how many different ways there are to complete each one of the individual tasks. Well, let's start with task 1. We said that the first 3 characters have to be a letter. That begs the question, how many different letters can I have here? We will say that there are 26 different letters that are available to me. Task 2 is also going to be letters, and task 3 is letters. That leaves the last 3 characters in my license plate that have to be a digit. In the decimal numbering system, there are 10 digits available to me. Now that I have my 6 tasks, I am going to use the product rule to multiply them together. And I'm going to use the product rule mainly because in a 6-character license plate, all 6 of these tasks must be performed. So I'm going to end up with 26 cubed multiplied by 10 cubed. And if I do my math right, my answer is 17,500. So we're going to get 26 cubed times 10 to the third. So I'll have 26 to the third times 10 to the third. And if I do my math right, this gives me just over 17.5 million unique license plates that I can have if this is the convention that the state uses to define license plates. All right, I'm going to give you a chance to work this out yourself. See if you can follow along. Let's pretend for just a minute that you are at Walmart buying some videos. You come up with a box that has 12 G-rated videos in it, a box that has 24 PG-rated videos, and a separate box that have 5 R-rated videos. So you're going to select 3 videos out of this group, 1 from each box, and the question is, how many different ways can you do that? We're going to call this the sample space. This would be the denominator of our probability. How many different ways can you draw out 3 videos, 1 from each box? We're going to call this the sample space. So if I can have a product rule, I can also have a sum rule. Where the product rule is breaking a procedure into sequential tasks, the sum rule is going to be breaking a procedure into mutually exclusive tasks. We're going to assume again that we have 2 tasks. I'll call them task 1 and task 2. And that there are n ways to complete task 1 and there are p ways to complete task 2. Then the sum rule would tell us that there are n plus p ways to complete the entire task. This is actually a logical OR. Think for just a minute. I can do one or the other. That is what mutually exclusive means. One or the other. An example of this might be, say, a final project. You're going to have to write a final program for the class, and you can pick you can pick a project from any of the 3 different programs within the School of Computing. Let's say, for instance, in computer science, there are 16 projects available. In the NET program, there are 17 projects available, and in the web program, there are 21 projects available. And you are going to be picking one final project. If I have 16 projects from CS, or I can pick one of the 17 projects from NET, or I can pick one of the 21 projects from the web program, I am going to add these together. 16, 17, or 21 is going to give me a total of 54 different options that I have available for my final project. That means that I have 54 different ways to choose my final project. So how do I decide if I should use the product rule or the sum rule? Think of the logical OR and the logical AND. When I state the problem, I can pick a final project from CS or from NET or from web. When I hear that logical OR, I think sum rule. Compared to the license plate example that we used before, a license plate must have 6 characters. So I choose the first character and the second character and the third character. To me, I hear that logical and it makes me think of the product rule. The same thing for the chairs in the auditorium. We had to pick a letter and we had to pick a number. And that logical and points me in the direction of the multiplication or the product rule. So we're going to come back to this project and your turn. And I'm going to have the same boxes of videos, but this time, instead of selecting 3 videos, 1 from each box, I'm going to have you select a single video from any one of the boxes. What is my sample space now? How many different ways can I do this? And is the value different than if I have to select a video from each one of the boxes? So next, we want to look at a process that might require us to use both the sum rule and the product rule together. So I know I presented you with the idea of a password, and you are the manager of the passwords, and your institution says that you can have a password that is 6 to 8 characters long, and that each one of the characters has to be uppercase or a digit. So how many different passwords can I have? We're going to see that this can be broken up into tasks. I'm going to define task 1 as passwords that are 6 characters in length. And then I'm going to define task 2 as passwords that are 7 characters in length. And task number 3 as passwords that are 8 characters in length. So I'm just going to focus my attention on this one right here, and I'll see if I can establish a pattern, and then we'll come up back to task 2 and task 3. But that begs the question, once I figure out the number of options available for task 1, task 2, and task 3, which of the operators, the sum rule or the product rule, am I going to use between the 3 of these? Well, it says that the password can be 6 or 7 or 8 characters in length. That would mean to me that I'm going to use the sum rule between the 3 tasks. So let's break task 1 down for just a minute. 6 characters in length. I'm going to say 1, 2, 3, 4, 5, 6 characters in length. Each one of these characters can be either an uppercase letter or a digit. This one I'm also going to break down into tasks. I'm going to say that each one of the individual tasks here are the number of characters that I can put in this space. So let's say for task number 1, how many different options do I have available to me for this first position? If I can have uppercase letters or digits, there are 26 uppercase letters, there are 10 digits. That means there are 36 options available for this first task. There are also 36 options available for each one of the remaining tasks, because each one of the characters can be either uppercase letter or a digit. That means I need to decide with these tasks, am I going to use the product rule or the sum rule? Well, if I have to pick the first one, and I also have to pick the second character, and I also have to pick the third character, I am going to use the product rule between these individual tasks because they are sequential in nature. That means I'm going to have 36 raised to the 6th power. So if there are 36 to the 6th ways to complete the first task with a 6-character password, how many different ways do you think there are to choose a 7-character password? Yep, that would be 36 raised to the 7th power. What about an 8-character password? That would be 36 to the 8. And we decided that we are going to add each one of the individual tasks together in order to get the total number of ways that we can complete the entire process. And I'm going to end up with a huge number. So this is an example of something that required me to use both the sum rule and the product rule. It actually required me to break things down into a series of separate tasks. I saw that there were 3 initial tasks because I had a password 6, 7, or 8 in length. And then I had to break down into tasks. How do I create, say, a password that has 6 characters in it? So I'm going to change up this example just a little bit. What if I have a password that is 6 to 8 characters long, made up of uppercase letters or digits, but I also add the constraint that at least one of the characters must be a digit? If at least one of the characters must be a digit, is this somehow going to change my ultimate outcome? Could I just come down here and say, okay, if at least one of them must be a digit, I'm going to put the digit here. I know that there are 10 digits that are available, which means that the rest of these 6 tasks are going to be 36. And what I would end up with is 10 times 36 to the 5th. Is this actually going to work for me? The answer is no. We're actually assuming here in this place that we have the single digit is in the first place. What happens if the single digit's here or the single digit is here? Each one of those would represent a different unique password. So there are 6 places that that digit could be. Could I just say that there are 6 times 10 times 36 to the 5th to account for the fact that that single digit can be in any of those 6 places. Will this one actually work as well? And the answer to this one is no. This one is not going to work either because we are duplicating possible outcomes. That means passwords with 3 digits and passwords with 4 digits. So it's going to take us a little bit different tact. So let me come at it from a different point of view. I'm going to say that, let's say for instance, we need exactly one number. I'm going to say for a minute that the number is here. If the number is in this position, how many characters do I have available for the second position? Well, it can't be a number. It must be a letter. So now I only have 26 options remaining for the last 5. This gives me 10 times 26 to the 5th. But we already decided that if I have exactly one number, it can be in any one of these 6 positions, which means that I need to multiply 10 times 26 to the 5th by 6 to account for the fact that can it be in any of the 6 positions. And that is for exactly one number. What if I have exactly 2 numbers? With exactly 2 numbers, I'm going to take for just a minute. I'll put the 2 numbers in these first 2 positions. The rest of the positions are going to have to be letters because we're talking about exactly 2 numbers. So now I see 10 squared times 26 to the 4th. But that begs the question, what if these 2 numbers happen to be in these 2 places? How many different ways can I put those 2 numbers in these 6 places? And we're going to see that there are 15 possible combinations, 15 different ways that I can put 2 numbers in exactly 2 numbers in 6 spaces. What if I have exactly 3 numbers? With exactly 3 numbers, I can, let's say for a minute that I put the numbers in the first 3 positions and I put the letters in the last 3 positions. I know that this is now going to give me 10 cubed times 26 cubed. That begs the question, how many different ways can I place those 3 numbers in a series of 6? We're going to see that the answer to this is 20. Now don't worry if you're not sure where the 15 and the 20 are coming from. We're going to be talking about that very soon. Now you might see a pattern developing. With exactly 4 numbers, there would be 10 to the 4, and then I'm going to have 26 to the 2nd. The total different ways that I can have 4 numbers, that I can place 4 numbers in 6 positions is 15. We'll do it again with exactly 5 numbers. That's going to give me 10 to the 5th times 26 to the 1st, and we're going to see that there are only 6 ways that I can put 5 numbers in 6 places, and then the last one would be exactly 6 numbers. That means all of the characters are numbered. So I'm just going to follow my pattern, 10 to the 6th. If all of them are numbers, I'll just include a 26 to the 0 because I'm seeing that a pattern has established, and there is only one way that I can order all 6 of those numbers into 6 different characters. So now when I add all of this up, I'm going to get a very large number. There are 1,867,000,000 ways that I can choose a password that is 6 in length that has at least one number. Now the keyword there was at least. When I see the at least, I think at least means exactly 1 or exactly 2 or exactly 3 or exactly 4. So I'm going to take each one of these individual tasks and I am going to add them all together. I'm hearing the or operator in my mind already. And that gives me the total number of ways that I can have a password 6 in length that has at least one number. Now there is a shortcut way that I can calculate this out. And the shortcut way, we're still working on passwords that are 6 in length. 1, 2, 3, 4, 5, 6. And the way that this shortcut is going to work is there are 36 possible options for any one of these given positions. But if at least one of them has to be a number, I am going to subtract off. Let's say that the number is here in this position. I'm going to subtract off the non-number values. That would be the characters. But maybe the number is here, so I'm going to subtract off the 26 from here. Maybe the number is here, maybe it's here, here, or here. And what I'm going to end up with is 36 to the 6th minus 26 to the 6th. And this value is going to give me the exact same number that I got when I calculated exactly 1, exactly 2, and so on. So this is a shortcut that I can use if I have at least one number and a password of 6. So then if I continue, we had, I'm pretty sure, 2 more passwords. Our original statement said the password can be 7 in length or the password could be 8 in length. If I follow that same pattern, I'm going to have 36 to the 7 minus 26 to the 7. Passwords 8 in length will be 36 to the 8 minus 26 to the 8. And then we're going to add these 3 tasks together to get an even larger number. So we have radically increased the number of unique passwords that I can have as the password administrator or the keeper of the passwords if I add one additional constraint. And that constraint is at least one of the numbers, at least one of the characters must be a digit. All right, so for your turn, this is an example of Weber State University's list of requirements for their password. It has to be at least 8 characters long, so between 8 and 32 characters long. There's at least one number, at least one uppercase, lowercase, all of this lengthy list of requirements. And not only that, then they make you change it at least every 10 to 15 weeks. It's not even every semester, but they force you to change your passwords. And I've worked at places that didn't allow you to have any of your last 10 passwords. But I'm not going to make you calculate the total number of passwords that you could have if you were the Weber State password guru. Instead, I am going to say that you are in charge of a university that says the password has to be exactly 8 characters long. It can have uppercase, lowercase characters, it can have numbers, and any of 6 symbols. I'm not going to define what those 6 symbols are, but I am going to say that it must contain at least one number. So your activity, the last activity, is to tell me how many unique passwords are available with this requirement.